hey there. I'm Alex Blick. I'm the Chief Engineer of Space Rocketry, which is the competitive student rocket engineering team at the University of Houston. Our team began 5 years ago in 2015, and ever since then, we have developed 2 competition rockets, and we've competed in the Spaceport America Cup for 3 years total. Today, we're going to be talking about our latest rocket, Oberon, which is a commercial off-the-shelf 10K solid propulsion competition rocket. Wait a second, I forgot my safety goggles. Be right back.
Hi there, my name is Emily Humble. I'm the project manager of Space Rocketry. So Oberon flies a low-key research M3000 motor, which takes it to an apogee of 9,800 feet. The airframe is entirely fiberglass, 6 inches in diameter and 10 feet long. The recovery system is dual deployment with the main and the nose cone and the drone about halfway through. These parachutes are deployed by black powder charges controlled by our flight computers. The primary is the Telemetron V3, which satisfies the GPS and telemetry requirements of the competition, and the backup is the Stratologger. Oberon's completed 3 flights in its history, 2 in the past year, the first at AAA Houston's South Site, and the second at AAA North Texas's Texas Shootout.
Oh, Emily, there you are. How's it going? All right, let's take a closer look at Oberon and see what exactly makes it fly. And also, always remember, safety first.
Alrighty, let's take a look at propulsion. Here's Irvin, he's our propulsion sub-team lead. What's going on, Irvin?
Hi guys.
Hey, Erwin.
How y'all doing?
Great. Good?
Yeah, this is Oberon's motor. It is a Loki M3000 from Loki Research. It is a 76 millimeter motor that has a total weight of 16 pounds, measures around 41 inches, and it also uses 6 ammonium perchlorate grains that burn in around 3 seconds.
Our first step for the motor assembly is to cut pieces of clear Scotch tape that have the circumference of the fuel grains. Start wrapping the tape between 2 green joints, one ensuring there are no wrinkles and that the tape does not overlap. Repeat the process for all 7 grains. While holding the grains at an angle, start pouring the epoxy and rubbing it on the grains. Make sure no epoxy touches the top or bottom of any grains. Then simply slide the motor liner from top to bottom. Leave about an inch of free space for the nozzle to fit in. Then grab your clear wrapping paper and place on top of the nozzle and insert it into the motor liner. Wait 48 hours to assemble the motor casing.
Huh. All right, well, thanks for that explanation, Irvin.
Yeah.
Hey you guys, getting back to work?
Thank you. Alright, let's take a look at what V's working on. He's our avionics sub-team lead.
Hello. So, due by IRAC rules, we have 2 flight computers, a primary and a secondary flight computer. For our primary flight computer, we're using the Telemetron V3 by Altus. We're using both the GPS and telemetry functionality. As our secondary computer, we are using the Stratologger CF by Perfect Flight.
Throughout this year, we've done a lot of testing, including pressure testing on both systems, GPS testing, and distance telemetry testing on Telemetron, and an integrated systems test to show E-match lighting capability. All of our wires are crimped. We use a pigtail connection to keep an airtight seal. We use terminal blocks on the inside and outside of the avionics bay, connecting to our 3D printed board using brass inserts to hold everything in place. We use screw switches on the inside to turn everything on, with a hole leading out of the airframe, and on the back of our board we contain the analysis subteam collecting SRAD data.
Alright, thank you, V. That was awesome.
Do you think you can help me out?
Yeah, sure.
Catch y'all later. All right, up next we have our sub-team lead, Ravi, to talk about the structures of Oberon.
Hey Alex, so Oberon is a 6-inch diameter rocket standing at 10 feet tall. The airframe is split into 3 sections: the lower airframe, the upper airframe, and the nose cone. Each of the airframe sections are made of G12 fiberglass, while the 4 fins are made of G10 fiberglass.
Yeah, okay, all right, yeah.
Our avionics bay, which is a 12-inch long G12 fiberglass tube, is placed in the upper airframe. The payload bay, which is made of the same material and is the same length, is used as a coupler between the lower and upper airframe. The drogue parachute is secured to the payload bay and stored in the bottom half of the upper airframe, while the main is secured to the payload bay is secured by 6 M5 machine screws. Flange nuts are epoxied to the inside of the bay, allowing the screws to secure the bay to the lower airframe. The avionics bay, due to its lightweight nature, is secured to the upper airframe through the use of 9 plastic rivets. Oberon uses two standard airfoiled rail buttons placed on the lower airframe. They are secured to the airframe through the use of two hard points, a 2x2 inch piece of plywood with a T-nut, which the rail button screws into. Oberon was painted by IA Coatings, a local company specializing in performance and protective coatings. As previously mentioned, Oberon has four fins which are secured to the airframe by our modular motor mount, which we'll talk more about later on.
Oh wait, I almost forgot about recovery. I think they're downstairs right now. Let's go see. All right, over here is our sub-team lead, Farida, to talk about our recovery system. Take it away, Farida.
Hey Alex. So the goal of recovery is to ensure safe landing and retrieval of the rocket. This way we can reuse parts of the rocket and analyze any data we collected in flight. This will help us with our future missions. And our dual deployment system features two parachutes released by two sets of ejection charges. Our drogue parachute is released from the middle of the rocket around apogee, and our main parachute is released from the nose cone of the rocket around 1,000 feet during descent. Our drogue parachute connects to our shock cord with the swivel link, and we use the quick link to secure this to the avionics bulkhead, which is then placed in the airframe, and we cover the charges with the Nomex blanket to minimize burns and tears in the parachutes or shock cords during separation. The main parachute is similar, except it is stored in a chute bag and uses a pilot chute to help deploy the entire 10-foot long nylon parachute. To prep the ejection charges, we use pre-measured amounts of Swiss 4F grains of black powder, place and pack thermal wadding, tape up each charge cup individually, and then tape around the circumference, and repeat 3 more times.
Okay, well that just about covers all the basics of Oberon. But next up we have a couple of key unique features about our rocket worth mentioning. Let's go take a trip up to the lab. Now, one of the cool features of Oberon is how we attach the fins. Come take a look at what we call the modular motor mount.
The modular motor mount, or MMM, is a custom fin can iteratively designed in order to increase the maintenance, versatility, and service life of Oberon. It also serves to grant modularity to both the fins and the motor. The MMM can accommodate any 76mm motor casing while also facilitating quick fin replacement, whether that's due to damage to the fins or edits to the fin's profile. Because the assembly is fully removable, maintenance can occur without any spatial constraints.
This is an older iteration of the MMM, the 2018-2019 MMM. One of the biggest differences is the material we use for the centering rings. They used to be thicker plywood centering rings. Another difference are the L brackets. These L brackets were non-modular, meaning they had to go and fit on a specific section of the centering ring and also go with specific fin.
Alright, let's hop on a call with our sub-team lead, Kelly, to talk about our scientific payload experiment.
Hi, Alex. Thanks for introducing the payload. In the field of aerospace medicine, physicians and researchers use medical knowledge and different technologies to understand how human physiology is impacted by flight. Exposure to different levels of gravity deviating from the norm of 1G can cause changes in tissue development and function, which is where Boris can come into play, the biological organism recording an integrated system. The payload's goal was to create a device in a vibration damaged chamber that could observe changes in biological systems during the flight of a rocket. This device would record a bred yeast cell culture to observe changes in cell diameter in microns on a mounted petri dish during the flight to make it possible to quantify the effects of large forces and pressure changes experienced by the cells. The device components are set up sort of like a microscope and include a 3D printed frame holding a GoPro with an attached 10x lens, a petri dish with a lid, a 10x lens above the petri dish for full magnification, neoprene foam inserts for dampening, an LED touch start light, a temperature logger, and 2 ice packs for temperature control. These pictures show our new and improved larger magnification lens and our cell cultures before our March and our May test launch. In the following video, we'll show you how it all comes together.
This is an overview of our device board, so you can see is inside a red frame with a press-on button at the bottom to illuminate the petri dish that we put in the center ring. The GoPro and the GoPro lens, plus the additional magnification lens, are in the top compartment. A lid goes onto the top of the metal frame that's secured with 4 nylock nuts on the steel rods that run the length of the frame. A button is there to turn on the GoPro along with the lens over the petri dish for magnification of the cells. the light at the bottom, and a ballast box for additional weight, as well as a temperature logger.
Thanks, Alex. Back over to you.
And lastly, we implemented an extra system in our rocket led by our analysis sub-team. And over here is our sub-team lead, Joao.
Hey, the analysis sub-team functions as an additional insight to the performance and design of Oberon. In the last year, we designed data capturing system for optimizing the recovery deployment system. Our project utilizes a TC 3.5 using I2C connections to communicate with specific sensors inside the avionics bay for data capturing purposes.
Well, now you know everything there is to know about Oberon. The only thing left to do now is put it together and see how it performs.
We have three main goals for the test launch. First, we want to prove the sufficiency of our design. Second, we want to see how accurate our simulations are and find areas of improvement. And lastly, we want to use this as an opportunity to truly prepare the team for a competition launch.
Our first test launch attempt was at the AAA Houston South side, and after encountering a couple of minor damages to the rocket upon landing, we refined our design and launched a second time at Texas Shootout, hosted by AAA North Texas. This time around, we had a near perfect flight, reaching 9,900 feet, which was only 200 feet within our prediction, and the rocket was recovered in perfect condition.
Yes, ma'am.